welcome to this explainer. Whenever we talk about space, black holes usually get lumped together into one big, scary monolith. We talk about them like there's just the black hole out there, one terrifying kind of object lurking in the dark. But as we're going to see today, that's not exactly true. What's actually out there is this incredibly diverse catalog. It's like a cosmic bestiary, ranging from stuff we've absolutely proven and even photographed, all the way to some truly bizarre anomalies that, well, only exist on paper. So today we're exploring the ordinary, the extreme, and the highly theoretical. Okay, let's dive into this. Here is our structural roadmap for today. 1. The standard core. 2. Galactic giants. 3. The missing link. And 4. Theoretical anomalies.
Starting off with Section 1, the standard core, stellar mass black holes. So this is basically our baseline. We're talking about stellar mass black holes born from the absolute collapse of massive stars. And get this, there are hundreds of millions of them hanging out in our galaxy alone. Let's break down exactly how these things come to be and how we actually find them. First, a massive star reaches the end of its life, right? Its core just can't pump out enough radiation pressure to fight off its own massive inward gravity. Second step, gravity wins. It completely collapses the star into this insanely dense object, usually packing somewhere between 3 and 100 times the mass of our sun. Now, step 3 is where it gets tricky, because the black hole usually just sits there. It's completely invisible in the vast, silent vacuum of space. But step 4 is the really cool part. We only actually see these invisible objects when a companion star happens to wander just a little too close and starts getting its gas siphoned off. As that stolen gas spirals down into the black hole, the whole system lights up violently, blasting out X-rays that our telescopes can finally spot. Oh, and by the way, despite what every sci-fi movie wants you to believe, these things are actually pretty harmless. Space is incredibly huge, and a stellar mass black hole is really only dangerous if you manage to get extremely close to it.
Moving right along to Section 2, Galactic Giants, the Supermassive Engines. Okay, so now we're scaling way up, leaving standard stars completely in the dust. The most crucial thing to understand here is that supermassive black holes, like Sagittarius A star right in the center of our own Milky Way, they don't just blindly vacuum up their galaxies. Take Sagittarius A star, for instance. It remarkably packs about 4.5 million solar masses into a space roughly the size of our solar system, and yet most stars orbit it completely safely from a distance. These giants are actually the architects of their galaxies. They can literally dictate galactic star formation, either actively sparking it into life or just aggressively choking it off entirely. When they're active, they drag massive amounts of gas into these accretion disks. The friction heats that gas up to millions of degrees, making it shine brighter than the entire rest of the galaxy combined. They also shoot out these mind-bending, inexplicable jets of matter into deep space at near light speed. And yeah, occasionally they cause what astronomers politely call tidal disruption events, which is just a very scientific way of saying they brutally tear a wandering star to shreds before it even reaches the event horizon. Now, I just want to let this next number sit with you for a second. 60 billion. That is the estimated solar mass of TON 618. It's one of the absolute most massive black holes we have ever discovered. 60 billion suns. Just to put that into perspective, the event horizon of TON 618 alone is wider than Neptune's entire orbit. You could literally take our whole solar system, drop it inside, and you wouldn't even be close to running out of space. It's a scale that almost completely defies human comprehension. And this brilliantly illustrates what happens when colossal masses like TON 618 start to spin. When they rotate at extreme speeds, we get this wild phenomenon called frame dragging. See, when a black hole spins fast enough, and some of these things push dangerously close to the theoretical speed limit of the universe, the actual space-time surrounding it gets literally dragged along for the ride. The physical distortion of reality is so severe here that even light can't just shoot straight outwards. It's actually forced to rotate along with the very fabric of space before it has a chance to escape.
But here's the catch. These absolute giants present a massive headache for astronomers, particularly the ones we're spotting in the very early universe, like just a few 100 million years after the Big Bang. We've got a genuine temporal anomaly on our hands here. It really makes us ask, how on earth does a black hole become so massive so incredibly quickly? Standard growth models say you need vast amounts of time to hoard that much matter. So mathematically speaking, there simply wasn't enough time for a tiny black hole to eat enough gas to reach billions of solar masses.
So to solve this cosmic detective mystery, scientists have put forward two genuinely mind-bending hypotheses. The first is that these early black holes were feeding way faster than we ever thought physics allowed. Basically, they were exceeding what's called the Eddington limit. Think of them as extreme cosmic speed eaters. Now, the second hypothesis, it's even wilder. It suggests they didn't start small at all. Instead, they formed directly from the collapse of colossal, impossibly dense gas clouds, completely bypassing that whole being a star phase entirely. If either of these turns out to be true, it is going to fundamentally alter our core assumptions about how the early universe actually operated. Which brings us to section 3, the missing link, intermediate mass. When you break down all these categories, a huge problem becomes incredibly obvious. There is a glaring mass gap. Down at the bottom, we've got stellar mass black holes, right? 3 to 100 times our sun's mass. And we know for a fact there are hundreds of millions of them. Up at the very top, we have these supermassive black holes weighing in at millions or even billions of solar masses, sitting right in galactic centers. But in the middle, intermediate mass black holes. These would weigh between 1,000 and 100,000 solar masses. And their frequency? They are rarely, if ever, found. And honestly, this is incredibly frustrating. If the supermassive giants grew from smaller seeds, they absolutely had to pass through this intermediate stage at some point. But they're kind of stuck in this blind spot. Too small for the techniques we use to scan those massive galactic centers, but way too big and rare for the methods we use to hunt down the stellar ones. So right now, astronomers are basically playing detective. These intermediate candidates remain completely unproven. We really only have hints, like faint whispers in the data from specific gravitational wave mergers, or maybe the weird agitated movements of stars in dense clusters that kind of suggest there's a heavy hidden core pulling on them. But until we actually find conclusive smoking gun proof, this missing intermediate link remains a massive hole in our understanding of how galaxies form.
All right, let's move into our final area, section 4. Theoretical anomalies, the stuff that exists on paper only.
Stepping completely away from proven observation, let's look at the ultimate theoretical contrast. You know a standard black hole. Everything flows in, absolutely nothing can escape. Well, contrast that with a white hole. I want you to imagine taking a video of a black hole and just hitting reverse. That is exactly what a white hole is. It's time reversed. It continuously spits matter out, and absolutely nothing, no matter how hard it tries, can enter it from the outside. The crazy thing is, mathematically speaking, in certain solutions to Einstein's equations, they appear almost perfectly. They often act as the theoretical exit point on the completely opposite side of a wormhole. But hey, before we get too excited about zipping through wormholes, let's bring this back to physical reality for a second. White holes, yeah, they likely do not exist. For one, they entirely lack any physical creation pathway. A black hole is born from a dying star, but a white hole doesn't have an origin story like that. And secondly, even if one magically popped into existence right now, the math shows it would be violently unstable. I mean, the absolute slightest external disturbance, literally a single photon hitting it, would cause the whole thing to instantly collapse in on itself and revert straight back into an ordinary black hole.
Okay, let's look at another anomaly, one that takes us all the way back to the actual dawn of time, primordial black holes. Think about it. At 0 seconds, the Big Bang happens. Just mere fractions of a second later, the universe was so chaotic and impossibly dense that early density fluctuations might have simply collapsed in on themselves. Now, this is crucial. Notice that standard stars didn't even ignite until millions of years later, so these primordial black holes could have formed without a dying star, without any prior history whatsoever. They were just born out of the raw chaos of the early universe.
And because they didn't have to rely on the strict limits of stellar evolution to form, their scale is absolutely wild. Theoretically, a primordial black hole could have virtually any mass you can think of. We're talking about ancient black holes that could have the mass of an entire mountain range, or on the flip side, be as infinitely small as a single speck of dust. And honestly, that massive variance leads us straight to one of the most provocative questions in modern astronomy. We all know dark matter makes up a huge portion of the universe, right? But we can't see it, we only feel its gravitational pull. So, is dark matter actually just a massive swarm of incredibly ancient, invisible, dust-sized primordial black holes pulling the strings of our galaxy? No one has conclusively detected one yet, but if they are out there, it would completely rewrite our entire understanding of reality. Thank you so much for joining me for this explainer. Keep looking up and keep questioning what's hiding out there in the dark.